Hi, I'm Andrew Malkov. If you watch my previous videos, you already have everything installed on your computer. You are ready to start working with Docker, whatever operating system you use. But before you can start, you need to understand some fundamental things about containers. In this video, I'm going to explain both the basic and advanced aspect of containers and Docker. At first, I will show you what are the benefits of containers. Then, I will talk about the main containers components and terms. After that, I'm going to dig inside the container image and container itself. And at the end, I will describe how Docker is architected and how it works. If you want to quickly jump to a specific moment in this video, you can use the timestamps that are in the description. Let's go back in time to the moment when containers revolution started. I'm talking now about containerization, which revolutionized transport and international trade in the second half of the 20th century. Can you believe that just 65 years ago there were no shipment containers? Loading and unloading cargo was completely manual work that was done by hand by longshoremen. Hand loading a ship was very expensive, about 40 times more than using containers, and took a lot of time. Another problem of that time was a small utilization of a capacity of the ship, because cargo size was not standardized. All this was changed by American businessman Malcolm McLean in 1956 and went down in history. Now we all know about shipment containers. Loading and unloading is a very cheap and fast process that no longer requires manual work. Container dimensions are standardized, so the ship capacity is fully utilized. The same container can be transported by ship, train, truck, and plane. I hope you are still with me and you don't think that you are watching the wrong video. Shipment containers change the world as well as the software containers, and they both have more similarities than you might think. In any case, the software world will not be the same again. Alright, let's look at the traditional organization that has four environments. There are development, testing, staging, and production. And there is a new application just released that needs to be installed on all of these environments. The operations team start with development environment first. So, they deploy an application, install all the required dependencies, frameworks, runtimes, and of course, configure all of them. After that, they switch to the testing environment, then deploy an application, install again all required dependencies, frameworks, runtimes, and again configure all of them. Then, they repeat this process again for staging and again for production environment. As a result, the operations team must spend 4 times the effort managing deployment of an application. And this is the case if all these environments are managed by the same team. For some organizations, there is a dedicated team per environment. So, in addition to the multiplied effort, they also add a lot of handover processes that increase the risks and costs even more and slow down the deployment process. The multiplied effort increases the risk to have the missing dependencies, versioning issues, incorrect configurations, and outdated runtimes. To mitigate this risk, an organization can start using containers. In this case, an application will be included into a package called a container image, which will also contain all required dependencies, frameworks, runtimes, and configuration. Then, this image will be used to create and run containers in all of this environment. In this case, there will be only single effort to manage the deployment of an application. So, containers are a solution to the problem of how to get software to run reliably when moved from one computing environment to another. This could be from a developer's laptop to a test environment, from a staging environment into production, and perhaps from a physical machine in a private data center to a virtual machine in a private or public cloud. In other words, if you have a container image, you can run a container with your application on any environment in just a couple of seconds. But wait, Can we do the same with virtual machines? Of course we can, but let's see how virtual machines work. There is a physical machine that has hardware resources like CPU, memory, disk, network interface, etc. On this machine, there is an operating system installed. Then, there is a hypervisor also installed, which is a software that virtualizes the resources and creates and runs virtual machines. Each virtual machine has a virtualized resources. It also has its own full operating system installed. Then, there are the dependencies of an application installed, as well as required frameworks, runtimes, and configurations. And finally, there is an application. And we have all the same for any other virtual machines. As you can see, in this design, there is a full operation system for each virtual machine. It is not an ideal solution. First of all, each operating system needs resources just to be up and running, so the utilization of the physical resources is not optimal. Another problem is that duplicated operating systems simply multiply the effort to maintain them, which brings no business value. And the last issue is that the full operating system significantly increases the size of the virtual machine image, which makes it impossible to spin up the new virtual machine very fast. Normally, it takes several minutes. So, containers are here to solve all these problems. Let's see how they are working. There is a physical or virtual machine that has hardware resources. On this machine, there is an operating system installed as well. Then, there is a container engine or runtime which takes the kernel of the host operating system and shares it to containers as a virtual operating system. So, all the containers share the same kernel of the host, and there is no need to have a kernel within a container. A container engine also manages container images and containers. I will give you more details about it in a minute. Then, within a container, there are the dependencies of an application, which includes as well required frameworks, runtime, and configurations. And finally, there is an application. And we have all the same for any other container. Now, when we see the both pictures, it is clear that virtual machines is more about virtualizing hardware, so each virtual machine is like a physical server. Container is more about virtualizing operating system with its own process tree, file system, network stack, etc. So, each container is like regular OS, but in reality, of course, it's not. Since containers not include the entire operating system, but only its application part, they are significantly smaller in size than virtual machines, which allow them to spin up in a couple of seconds comparing to a few minutes for virtual machines. And the last advantage is that the containers require less hardware resources to operate, because they are sharing the same kernel from the host operating system. I hope it is now clear that the containers are there to change the way we distribute and deploy our applications. That's why Gartner predicts that by 2022, more than 75% of global organizations will be running containerized applications in production. So, let's take a closer look at the components involved into the process to run a container. The first component is a host, which might be a physical or virtual machine that runs the containers. It could be your laptop or a virtual multi-core server in the cloud. There is a client installed on host, which is responsible to provide us the easy way to communicate to a container engine. So we use a client to send the commands to a container engine and get the results back from it. A container engine is responsible for managing containers and also container images that are stored locally on a host in a local cache. You can think now that the container image is a deployment package of an application, and it contains everything that is needed to let this application run. I will give you more details about an image in a couple of minutes. Using a container image, a container agent can create and run a container. A container is an isolated area of operating system with resource limits applied to it. In other words, container is a running instance of a container image. And the last but not least component is a container registry, which is just an external storage of container images. I draw it as a cloud not because it's always a cloud service, but just to show that usually it is hosted outside of the host. So it is an external service. Now, when all the components involved into the process are defined, let's see how they are working together. Let's imagine that I want to run on my host an application that was packed as a container image. So I use a client to type a command to run a container. A client sends the command to a container engine. A container engine will look at the local cache to see if it already has needed container image. If an image is not there yet, an engine will search for it in a container registry. And if it's there, then an image will be pulled, or in other words downloaded, and stored in a local cache. Then a container engine will use this image to create a container and run it. If I send a command using a client to an engine to run the same application again, it will find the container image in a local cache and use it immediately to create and run a new container. And if I ask for the same again, it will do it again and again, and again if needed. So, as you can see, I can run multiple containers on the same host, and they can be based on the same image or completely different container images. Now, let's take a closer look at the container image. Many people think that a container is a distribution or a deployment package of an application, but actually it is not. A container image is that package. It splits into several layers. These layers contains everything needed to let an application run: an application itself, its dependencies, a runtime, an operating system files and objects. For example, if you look at the container image that is built for a Node.js application, it might contain an application layer, npm packages layer, Node.js runtime layer, and an Alpine Linux OS files and object layers. Each layer has its unique ID, which is in fact a hash generated from its content. This hash has two purposes. Firstly, it allows to uniquely identify a layer. Secondly, since it's a hash, it guarantees security, so it's impossible to change the content of a layer unnoticed by a container engine. Because when content of a layer changes, its hash will change as well. Then a container engine will see it and treat the modified layer as a new one, which will not be used to create a final container. That's why the layers are read-only. All of the layers inside an image are ordered. Every layer except the last one references the layer below. It's a very important aspect, because here I'm talking about unified file system. For example, if two or more layers have a file with the same name, the layer on top gets priority over the bottom layers. So, the resulting file system of a container will be built from the bottom up. A container image also contains a manifest, which is a JSON file that explains how it all fits together. Now we understand what is an image, and it's time to look at the container itself. Linux containers have been around for ages, well, at least the kernel stuff that we used to build them. Some high-tech companies, like Google for example, have been using containers for a long time, but for most of us they were just too hard. We use two main building blocks when we are running containers: namespaces and control groups. Both of them are low-level OS kernel primitives. Namespaces are about isolation, and control groups are about grouping objects and setting limits. Let's look at the namespaces first. In Linux, we have these namespaces, and the container is an organized collection of them. A container is its own group of these namespaces, and this group is isolated. So, each container is its own group. PID gives each container its own isolated process tree, so it can't see that other containers exist. IPC allow containers to use the same shared memory, but it blocks everything from outside of it. MNT gives an isolated file system. Net gives a container an isolated network stack. UTS gives every container its own hostname. User gives an ability to map an account inside a container to different users on a host that allow us to have a root user inside the container who is not a privileged user on the host. So, the main idea of namespaces is to provide an isolation, but an isolation is not all we need. Do you remember? I told you that I can run multiple containers on the same host. But a host, whether it is a physical or virtual machine, has limited amount of hardware resources like CPU, memory, and disk. So, there is always a fear of noisy neighbors. What will happen if one of the containers consumes more and more memory or CPU? Of course, it will affect the performance of all other containers. So we need to have something to limit the consumption of system resources. In Linux, it is control groups, or just shortly, C groups. We use them to group processes and set limits. So, control groups let us apply limits to each container separately to control consumption of CPU, memory, and disk I/O. So, if we take namespaces and add to them C groups and add a unified file system, we will get a modern container. And this is exactly what Docker did. Docker came and made all of it for us easy. Let's see what components Docker has and how they work together. Previously, Docker was a monolith that has everything inside. Nobody was happy about it, that's why Docker was re-architected and divided into multiple components. Right now, it contains Docker CLI, which is a command line interface that we use to run commands, Docker daemon, or shortly Docker D, that exposes an API, Containerd, which is an industry standard container runtime that manages containers, images, storage, and network interfaces, and runc, that is executor for containers. So, if I want to run a container, I run a command using Docker CLI. It will send HTTP request to a REST API of Docker daemon. Then, Dockerd will do a call to a Containerd using gRPC, which is a powerful framework to work with remote procedure call. I'm not going to talk about it in this video, but it's a hot topic now that deserves its own series of videos. Okay, where are we? Then, Containerd starts shim process for every container where runc creates a container and then exit. So, runc is called for every new container and it doesn't stick around, but shim does. Phew. I know, it was not an easy video with a lot of information and details, but please, don't worry if some concepts are still not completely clear for you. I will do my best to make them more and more clearer in my next hands-on videos, so subscribe to my channel to not miss them. For now, you just have to remember that to start working with Docker, you need to have Docker engine installed on your host, and you will use Docker CLI to send your commands to Docker daemon that will manage your images and containers. A container image is a deployment package of an application, and it contains several read-only layers which have their own unique ID. These images are stored inside a container registry, for example Docker Hub, and they should be downloaded into a local cache on a host before Docker can run a container. And finally, a container itself is a running instance of a container image. So, with this explanation in mind, you are ready now to start running containers using Docker. But how to do this is the topic for my next video. Please subscribe to my channel to not miss it. Thanks for watching and see you soon. Can you believe just as Can you believe that just that just can you believe that that's that just can you believe that just 65 years ago there was no can you believe that just 65 years ago can you believe that 65 years ago there was no